My name is Ignacy Stepka. This summer, I was working with Dr. Nicholas Gisolfi and Dr. Arthur Dubravsky on formal verification of Bayesian network classifiers using decision diagrams and propositional logic. First, I would like to start from our motivation. With the widespread of AI these days, we would want to be able to deploy machine learning systems to also more safety-critical real-world applications. Some examples of safety-critical applications are, for example, hospitals, planes, or cars. But to be able to do that, we want to make sure that our model will never inflict any harm that would be otherwise easily prevented by an old system that was in this place before. We also want to be able to do all of that because modern machine learning systems pose a great opportunity to improve many processes in the real world due to their strong predictive capabilities. In our work, we focus specifically on verifications suited for Bayesian networks. The practical application that drives our work is a problem of triage in mass casualty incidents. Triage is a problem of ranking the casualties by the severity of suffered injuries in order to enable optimal medical treatment delivery. Therefore, it is clear that this scenario is of life critical importance. Having said that, we want to enable responsible development of AI models to ensure their robustness and especially trustworthiness. Knowing the life importance of this kind of task, we also want to be absolutely sure that the model does not make mistakes in scenarios that we can foresee. Our approach specifically is to take a Bayesian network, a probabilistic model, and compile it into an equivalent form of symbolic and tractable multi-valued decision diagram. Decision diagram is a simple structure where a vertical path through nodes, indicated here with a yellow arrow, is a trace of particular prediction. This representation is a useful step towards rigorous verification of our Bayesian model as we get rid of the probabilistic structure. Next, after we obtain the decision diagram, we want to transform it into a form of Boolean algebra formula. This is an important step towards having a strict formalism that allows to perform rigorous proofs. Therefore, we introduce an encoding scheme and convert the diagram into a form of Boolean algebra, specifically CNF. Having the model encoded in Boolean algebra form allows us to run verification queries. The first query that we introduce is if-then rules. This verification task aims to enable experts to ask simple questions about the model and check whether model adheres to some specifications that they have in mind. On the left here, we show an example of such query. This input in form of if-then rule is transformed later into the CNF form and later proved with a SAT solver. In the process, we change the query to its negation in order to perform the proof in a proof by contradiction manner. This specifically allows us to enumerate counterexamples in case of the lack of adherence to the query. Such enumeration of counterexamples is helpful because with them we can show these examples to experts and ask whether such behavior is expected or whether we should maybe change something in our model or edit some relationships. The second verification query that we introduce here is monotonicity. With this verification query, we simply want to ask the model whether a given feature X interacts monotonically with the outcome variable Y. For this query, we can also enumerate counterexamples and show them to subject experts. Here on these slides, we present a small summary of the efficiency of our proposed approach, benchmarked on 6 popular Bayesian network models. These results show that the most of the compute is spent on the first step, which is compilation step. This is an expected behavior as the algorithm is of exponential nature. But the plus is that each network has to be compiled only once, and after that, it can be asked an infinite number of verification queries, which themselves are quite fast and do not stand for a large computing effort. Wrapping up, with our work, we show that the proposed formalism is sufficient to verify some safety-critical properties of Bayesian networks. Our work is definitely a step towards building systems that are capable of autonomously producing models and deploying them while ensuring safe and reliable performance. This work addresses the unmet needs of verification and validation processes for AI, which are paramount to the widespread adoption of AI. And lastly, we perform the exact verification on Bayesian Networks classifiers, which is a more rigorous approach than performing a probabilistic verification. Thank you for your attention. I would like to take a moment and also thank all the people behind the RIS program, especially Rachel Bursin and Dr. John Dolan. I want to also thank my advisor, Dr. Dubravsky, who always asked many interesting questions and made this research possible. I also want to thank my mentor, Dr. Nicholas Ghisolfi, for mentoring me in this research effort and helping me throughout the project. And at the end, I want to thank all the members of Autumn Lab for accommodating me here in Pittsburgh and supporting me during my research efforts. Once again, thank you for your attention.